Hello everyone, welcome to today's tutorial on Yebo Physics, where we are looking on a chapter on laws of motion. So this is a recap of the chapter that you have already covered. So we'll simply go through the few questions for this session and see how far we can go. So I hope you can hear me loud and clear from wherever you are. And yeah, thank you for joining us. If you are with us live, we appreciate and would like to hear your comments or your contributions throughout the session. So please feel free to interact, feel free to participate throughout the activities that will benefit you in a unique way. Okay, so what we have here is part 3, question number 11, the questions you find them on Moodle. And this question goes, in the figure shown, the coefficient of kinetic friction between the block and the incline is 0.29. What is the magnitude of the acceleration of the suspended block as it falls? Disregard any pulley, mass, or friction in the pulley. So this is the condition given. We are going to neglect friction at the pulley or the mass of the pulley in this calculation. So the question is referring to the diagram that's showing on the screen right now. And this is a diagram where we have an incline of 30 degrees from which a 2m mass is pulled down the incline, which is connected to a hanging mass of value m. So now what the question requires us to do is finding the magnitude of the acceleration of the suspended block. So the important thing to note in this case, given a diagram like this, is that we can identify forces acting on this system. We have forces that would act on this system. If I can redraw it, the pulley, the 2m mass, the string, and the 1m mass. So identifying forces that act on this system would have tension, which pulls in this direction, and this tension is the same because the string is a light inextensible string, so it will have the same tension throughout, but the directions of the tension are such that the tension pointing upwards, that is along the vertical part of the string, will be holding the mass that tends to have a weight downwards, and the tension that's on the incline, mass on the incline, is pulling towards the pulley as well, such that it acts against another force, which is a frictional force. So we have a frictional force there. So these are the forces we can identify down the incline. Vertically, there is another weight, 2W, and at an angle theta to it. So we're told this is an angle theta. So that will be 2W cos theta. And then which means this 2W cos theta is perpendicular to the incline. So that will be the force that relates to the normal to the surface. So while we look at those forces, we know that given the coefficient of friction, the frictional force Fr will be equal to mu k times n. Mu k times n. So that will enable us to find the value of Fr. Okay, so basically that's everything given from the question. We've just identified the forces, and these are the forces that we're going to deal with. So now, since the mass is hanging, the mass that has a weight W is hanging, it will consider the downward direction as positive. That's up to us to decide. So I'm choosing the downward direction as positive. That leads us to an equation, W minus T equals to the mass times the acceleration. So that's just for the first part of the motion, which is vertical. The same we do for the incline, where we have T, the tension. So in the direction of the acceleration, remember, I've chosen this direction to be the positive. So the acceleration in this case is in the direction of the weight. So the same would apply if acceleration is to be in the same direction. That means the tension T minus Fr minus a component, no, there's no component in the Fr, but this is plus a component of the weight down the plane, 2W sine theta will be equal to 2m times A. So these are the two equations we can come up with from the given setup, such that we need to find the acceleration, so we need to eliminate some of these terms. So how do we do that? So I'm gonna redo that again. So I'll call this equation 1 and this equation 2. So from equation 1, we know the weight is mg. So that's mg minus T equals to ma. That's from 1. And the other equation says 2mg sine theta. So it will have T minus ft minus f, we said is mu n, where n is, what is n? Remember this along the perpendicular to the incline, the component of the weight will balance up with the reaction n. So n is equivalent to 2w cos theta, which is 2mg cos 30. Then that's the part for, remember, we have this is just the part that we've dealt with, Fr, the friction. So it is mu n, where n is 2w cos 30. Then the next part is 2w sine 30. So that one adds plus 2mg sine 30 equals to 2m times A. So those are the equations that we have, and what we can do is add equation 1 and 2. So this is still equation 1, that's equation 2. If we add the two, what it simply means is we get a sum of these, which is mg minus T plus T. So this, I'm dealing with the left hand side first. So mg minus T at that T minus 2 mu mg cos 30 root 3 over 2 plus 2 mg sine 30 is half. Then this is equal to the right hand side, ma plus 2ma is 3ma. So this makes it simple because we know these are like terms, and because they have opposite signs, we can cancel them out. It's even nicer that we have terms in all terms given with m on them, so we can eliminate that m by dividing by m. So that's just dividing by m throughout. What we remain with is g minus 2 mu g root 3 over 2, where we can cancel out this 2 and that 2, plus this and that can cancel out, which is plus g again, equals to 3a. So the value of mu was given there, 0.29. So we've got 9.8. 9.8 plus 9.8, which is 9.8 times 2 minus 0.29 multiplied by 9.8 multiplied by root 3 equals to 3a. So let's see what we get from that calculation. What do we get from that calculation? That's 9.8 by 2. 9.8 multiplied by 2. And I want a bracket there. Subtract. Root 3 times 9.8 times 0.29. So open bracket. 0.29 multiplied by the square root of 3 multiplied by, no, not like that, go out of that root sign and then multiply by 9.8. That's enough. Close that. Then divide everything by 3. So divide everything by 3. So I have 4.89, which is 4.9. So this gives me 4.89 meters per second squared equals to A. So this is the acceleration I'm getting there for the system. So this will be the acceleration we get for the system, and there is our 4.9. So we're 4.9 meters per second squared. So that's how to deal with such a question given the pulley system and a hanging mass. We should know that the tension in the string is the same if the string is light and inextensible. Then neglecting the friction from the pulley and the mass of the pulley, that would mean the forces that we consider are the forces on the hanging mass, which is the tension and the weight, and the forces on the incline, which is friction, the tension, and the component of the weight along the incline. So that is very important for the construction or development of the equations that you can work with. Okay, I see we have a few guys connected online. How are you guys? It's good to have you. Can you just say hi on the chat, or maybe unmute your mic? We're live on YouTube, and we still have the Teams platform up and running. So if you can chat with us, we'll be very, very glad to hear you from wherever you are. So if you have any questions, again, feel free to ask. We are here to assist you in every way possible. We'll try our best to help you in every way we can. Okay, so that's it about that question. Let me just scroll down to the next question, number 12. It says something about the coefficient of friction again. Okay, we shall proceed to our next question. The coefficient of kinetic friction, yes, between the surface and the larger block is 0.25. So there's a diagram there which is being referred to. I'll just give you a glimpse of the diagram, which is this one, a simple diagram. It's a force acting on a 2m mass, which is in contact with a 3m mass. So those are the two blocks. So the coefficient of kinetic friction between the surface and the larger block is 0.25, and the coefficient of kinetic friction between the surface and the smaller block is 0.4. If F the force that's pushing the 2M block is 22 newtons, and M, the mass referred to in either block, is 1 kg. In the figure, what is the magnitude of the acceleration of either block? So one thing for sure, the two blocks are in contact. When they are pushed by a force F, they should move together, with the same acceleration. So surface, 2M block and 3M block in contact with it, like that. Okay. So the force is a 22 Newton force. F equals to 22 newtons. That is given. Then 2M will be 2 kg, 3M will be 3 kg. But we know that for the 2M mass, mu k, for the 2 kg mass is 0.4. And mu k for the 3 kg mass is equal to 0.25. Okay. So that's all the given information. Now we need to find the magnitude of the acceleration of either block. Remember, acceleration is a result of the net force. So what we do there, F net will be equal to the force, the 22 Newton force, minus the frictional force on the 2 kg block, which is mu k2, times the normal on block 2, on the 2 kg block, minus mu k3, that's a subscript, sorry, times n, the normal on the 3 kg block. So this will be 22. And anyway, F net will be the mass times the acceleration. So that means this expression equates to the 2 kg plus the, okay, so let me call it 2m plus 3m. Everything multiplied by A. 2m plus 3m, everything multiplied by A. So that means we can say 2m, m is 1, so it's 2 plus 3 multiplied by A, that's F net, is equal to 22 minus mk2, we said mk2 is 0.4. The normal is equal to, so we've got a weight there, due to 2, and a normal, and 2. These are equal but opposite. The weight due to 3 will be equivalent to the normal due to 3. So mk2 being 0.4 multiplied by the weight 2 kg times g, which is mg, 2 times 9.8, like that, multiplied by 0.25, minus 0.25 multiplied by 3 kg times 9.8. So we have our equation like that in terms of A. So divide by 5. Okay, before we go there, let's, so this is 5A equals to 22 minus 0.8 times 9.8 minus 0.75 times 9.8. So A will be everything over 5. That's our expression we can use to find A. So let's do that. Fraction 22 minus 9.8 multiplied by 1.55. So if you add 0.8 and 0.75, that's 1.55. 1.55, close bracket, everything divided by 5. 1.36 meters per second squared is our acceleration. Okay, so remember what is important is coming up with the equation, and this equation we know the forces are vectors. So the force to the right is a positive force, and the forces that we have subtracted, these are forces opposing the motion. They are frictional forces, so we subtract them, and the result is the net force, which is the total mass, because the two blocks are in contact. So their total mass times the acceleration. Each block will move with the same acceleration as a unit. So once you do that, the rest is the mathematics, where you plug in the numbers and solve for A. Okay. So we can now move on to the next. Did I check this? Okay, I needed to check that. 4.9. That's okay. And for this one, what did we get? What did we get? 1.36. Rounded to two significant figures. That's 1.4. Okay, the vector sum of three coplanar forces. This is not a calculation question, so you need to know your stuff when it comes to facts. So if you have three coplanar forces, their vector sum must be 0. Is it true? Must it be perpendicular to one of the three forces? Or it must be parallel to one of the three forces. It must be perpendicular to the plane. It may have any direction in the plane. So three coplanar forces will look like they are just forces in the same plane. They can be like this. So their resultant must it be parallel to one of the three forces, perpendicular to the plane, or perpendicular to one of the three forces, or is 0, or in any direction. So the proper answer is that, because it will depend on what's the magnitude of each of the forces and the angle at which it acts. So it can take any direction. The resultant can take any direction. So if you take F1, after F1 add F2, so that's F1 like that, plus F2 in that direction, plus F3 in that direction, right? Their resultant can add 0 if they make a closed triangle like that. Their resultant can be 0. But the perpendicular to one of the three forces, it's not, the resultant doesn't necessarily need to be perpendicular to the three forces. It doesn't necessarily need to be perpendicular to one of the three forces. So that one does not make sense. Parallel to one of the three forces, again, it can, but it's not always the case. So the one that is general and ideal for any given case is where the resultant can have any direction. So this is a special case where it can be 0, but the rest are not acceptable. Okay. This is question number 14, which looks at circular motion. So when it comes to circular motion, one thing you need to be aware of, to be cognizant of, is the fact that in a circular motion, the acceleration is towards the center. That's number one. Then, so such that this acceleration gives us the direction in which the velocity is constantly changing. So it can be a constant speed. So we can have velocity in that direction, whose magnitude is constant throughout at any point. So the magnitude of that velocity there, v, so let's say point A, where VA, point B, where VB, and point C, where VC. The magnitude of VA equals to the magnitude of VB equals to the magnitude of VC. These magnitudes are basically speeds. What makes them different are the directions. So the change in the direction is what accounts for the change in velocity, which gives us an acceleration. And that acceleration is centripetal acceleration, which is towards the center. This centripetal acceleration, if we have a mass at that point, then which means the centripetal force, Fc, will be the mass times the centripetal acceleration. This centripetal force is a resultant force. It's a resultant or a net force after considering all forces acting on that mass. So this is a net force. It's a net force. In other words, this is not a type of force which you can include in the free body system. Okay, so what are we saying now? We have this acceleration A given by by v squared, v squared over r, or omega squared r. So that's how we calculate that acceleration. Okay, so that's just a summary. Let's look at the question. So the question says a 50 kg child riding a Ferris wheel of radius 10 meters. So if we're given the radius is 10 meters, traveling in a vertical circle similar to the one I've drawn, the wheel completes one revolution in every 10 seconds. So 1 rev per 10 seconds means we have 0.1 revolutions per every second. And this means our omega will be 0.1. A revolution is 2 pi times 2 pi per second. So this gives us 0.2 pi radians per second. That's the angular speed. The rate of the angle swept, or the rate of sweeping the angle, or change in the angle. Okay, so now, having been given that angular speed, what is the magnitude of the force on the child by the seat at the highest point on the circular path? So now we are at the highest point, similar to point A. Then we have said that what we want is the force on the child. So this is the situation. At the top of the wheel, we have our child there. Ideally, they'll be sitting on the Ferris wheel. Okay. So the child is sitting there, and the wheel is rotating like that. The center is there. Okay. Okay, so that's the big wheel. And what we have here is the weight of the child downward. And because there is a force keeping the child in motion, that force is coming from either the weight and the reaction, but also we know that we have got the net force, Fc. So let me put the W on the other side. So the weight. Then we also have the resultant, Fc, in that direction, which is the centripetal force. And we can think of the normal depending on what is keeping how we have to keep the child within that loop. We could have our normal in the upward direction, or the normal could be on the downward direction due to the belt that holds the child to prevent the child from escaping or from being tangentially thrown off the wheel, maybe we can say. So ideally, let's start with this. Let me change the color. I don't want that one. I'll use a different one, black. Yes. So the other force is the normal. So the main forces acting on the child are the weight and the normal. Constructing equations would mean W minus N is equal to Fc, the net force. Right? And this net force is the m omega squared r. So W is mass of the child again times gravity, and N is generally the normal, which is the force that we need to find, the force that's acting on the child. So this is the force that's acting on the child by the seat. Okay, so now what it means is mg minus m omega squared r equals to n. And we know m is 50, g is 9.8, and 50. We said our omega is, where did we, 0.2 pi radians. So that's 0.2 pi radians per second squared times r, which is 10, equals to n. Okay. Now, what do? We do the enumeration. There is my calculator. 50 by 9.8. Subtract 50 by 0.2 pi squared by 10. So that's 500 multiplied by open bracket 0.2. Where is pi? There is pi. Close that bracket, square that, and there is 292. So we have 292.6 newtons equals to the normal. So that's 292.6. And that's 0.29 kilonewtons. In kilonewtons, that will be our solution. Okay. So what is important to note, I'll re-emphasize this, important to note is the fact that the centripetal force is a net force. So always it is directed towards the center, meaning after every force that's acting on your object that is in circular motion is considered, the resultant of those forces acting on that object in circular motion will be, excuse me, sorry. So the resultant of the forces that are acting on that object that's in circular motion is that centripetal force that is always towards the center, hence keeping the object in circular motion. Okay, so in other words, if we are to consider an object that is at the bottom, is still W, and the normal will be the one contributing to the centripetal force, such that Fc, our resultant, will be towards that direction. So Fc is what tells you what's happening between those forces. So in other words, if we say N, we would say N minus W in this case equals to mv squared over r, or m omega squared r. So in this case, this is when this is at the point where the object experiences, or if it's a human being, they will experience the greatest force, because N will be equal to W plus m omega squared r. Whereas in this case, it was W minus N was equal to W, where is it? Yeah, weight minus m omega squared r. So this one is quite less at the top as compared to at the bottom. All right, I think I'll pass on that one. That should be quite clear. Then a rock attached to a string swings in a vertical circle. Which free body diagram could correctly describe the forces on the rock when it is at the lowest point? So we have a rock attached to a string, swinging in a vertical circle. Then now we are given which free body diagrams given here would describe best the forces on the rock when the rock is at the lowest point. So that's just a rock there. We know with tension and the center of that vertical, we can call it O. Then the rock with the weight W. Do we have any other force acting on this? Can you think of any other force? Remember, this rock is being swung around like that to give that kind of motion. Okay, something like that. So if that's the path that the rock would follow. Okay. Then what other forces could be acting on this rock? Are there any other forces acting on the rock? So A just shows one force. That's not correct. B shows T and W. I think that's more like what we have there. C shows T. D shows T and N. So N is like a normal force, which is downward there. It's quite weird. Then E is showing TW and another force F to your right. So remember, in terms of forces, right? In terms of forces, there is no acceleration in any direction other than in the vertical. It means since this block is this rock would be moving with a constant speed, around the circle, it doesn't have any component of acceleration tangential to the circle, because tangential to that circle, the speed is always constant, right? So there's no net force. There's a balance of forces which result in a constant speed throughout the motion perpendicular to the radius of the circle. So tangential to that direction, there is no force. The force is, okay, if we don't consider resistance anyway, it simply means there is equilibrium, and in this case, there are no forces whatsoever. So the only acceleration is towards the center, where the net force is acting as a result of those two. So this is a distractor. That F there would not make any sense in this case. So our best choice will be to have B. B is the best choice. Okay, so that's it for these questions on motion in one direction and motion. Okay, that was sorry, for Newton's laws, and circular motion. Do we have any questions? So if we don't have any questions, thank you once again for joining us. We'll be live again in the coming week for more tutorials. So please feel free whenever you are available to join us and interact with us on the platform. So if you have any questions, we are on the platform every Tuesday, Wednesday, and Thursday normally, unless there are any other kind of glitches that would have caused us to shift our times. But otherwise, I would advise you also to subscribe to the channel, so that if we are live and you have not received any notification via email, you can still get the notifications via the channel. So thank you for joining us. Keep well and all the best with your studies. Bye-bye.